the factor theorem here, we have to figure out which one of these parts of the factor theorem are we using. We're told to factor, so we're going to look at part B. Part B says if x minus 2, because that's the case here, if x minus 2 is a factor, then I should be able to put the value of 2 into my function and come out with a 0. And if I don't get that, then it's not a factor. So that's what the factor theorem helps us to decide. So let's try that. Now we're going to say, okay, if x minus 2 is a factor, then I should be able to take the 2, plug it into my function, and come out with 0 in the end. Because we're used to seeing that value as our x-intercept, right? 2, 0. If it was a factor, it'd be an x-intercept. So let's see if we get 0 here. We get 8 plus 2 times 4 is 8, minus 2 minus 10. That's 16 minus 12. That's 4. So 2, 4 would be the point on this function. It's not 2, 0. It's not a 0 of the function. Therefore, it is not a factor. So x minus 2 is not a factor, since f of 2 does not equal 0. So that's how you would write your conclusion based on the information that the factor theorem gives you. Okay, so that's using part B. This uses part B of the factor theorem. And now, if we look at 8b, we're looking at this polynomial function. Now we're saying, use the factor theorem to factor that thing, actually factor it. Well, our usual techniques of how we factor a second degree, well, first of all, it's not a trinomial. It doesn't have 3 terms, so we can't use our usual little way of backwardsing FOIL here. And it's not the difference between 2 perfect squares. That's not going to help us to factor it. So I got to have something else to help me factor this, and this is where the factor theorem comes in. So what can we learn about the factor theorem? The factor theorem part A tells us if we can find a number, C, or maybe more than one number, when I set this equal to 0, voila, I'll have my factors. So how do I go about finding my factors for this? What do I have to do first? Someone other than Katie Woods. What would I do to try to find a factor? Anybody? Caitlin? Set it equal to 0. Find the zeros of the polynomial function. Remember, if I know the zeros, I know the factors. So now I'm going to set this equal to 0, and I'm going to solve this equation. Well, this is a quadratic equation. So you can either use your square root property, but if you do that, you're going to forget one of them, I guarantee. So I'm going to use the quadratic formula. B is 0, plus or minus b squared is 0, minus 4 times 2 times negative 3 is c, all over 2a. So that gives me 0 plus or minus the square root of, let's see, 4 times 2 is 8. 8 times negative 3 is negative 24. So I get 0, 0, take away negative 24. Bless you. Are you allergic to something in here? Oh, you sound so stuffy. And I get 0 plus or minus the square root of 24 over 4. So now we just got to remember how to simplify the square root of 24. And just a little review. You break 24 up into a product where one of your factors is a perfect square. Square root of 4 is a perfect square. So this is 2 square roots of 6. So I get 0 plus or minus 2 square roots of 6 all over 4. The 0 in front is doing absolutely nothing. So I got 2 answers here. X equals 2 square roots of 6 over 4, and x equals minus 2 square roots of 6 over 4. And when I simplify that, when I reduce it, I have a common factor of 2 to the top and bottom. So I get the square root of 6, oops, over 2, and negative square root of 6 over 2. So if I were to write this, notice these always come in pairs. Irrational roots or zeros always come in pairs. One's a positive, one's a negative. So if I were to factor this now, and here's the tricky part, here's my polynomial function in my polynomial form. What's my leading coefficient here? What's my leading coefficient? 2, right? Do you need this, Sam? All right, so my leading coefficient here is 2, and that means it's going to be the same leading coefficient when I factor this. Because this is a quadratic, it's going to have 2 sets of parentheses to the first power. They're both going to be linear factors. This is what it would look like. X take away the square root of 6 over 2, and x take away a negative square root of 6 over 2. And remember, we simplify that to look like this. When we have a negative 0, we change our subtraction sign to a plus sign. Okay. So suppose you wanted to check this to make sure it really looks like this. You want to check it. How would you go about checking this to see if you can get back to 2x squared minus 3? What would you do? How would you start it? Would you be afraid to start it? Do you think you have the algebra skills to multiply that out? Say yes, I do. Yes, you do. How would you start this? You're multiplying 3 things. So where do you start? Nobody can rescue anybody? So if I told you on the final to multiply this out, you wouldn't be able to do it? I'm not letting you answer, Katie. See if you can get your rest of your classmates to think a little bit about it. Well, we got a long class today, but I'll wait. I'll wait for someone to take a risk here. The 2 Katies can't answer. Okay, we'll leave it then. So I would advise you in your spare time to multiply that out. And if you can't, see me or see your tutor or come to the studio. Okay, so did we get to number 9? Yes, Chris?
So if 2 is A and the power that x is 2 is n, and then negative c, like n to the root of negative 1 times b over a, also solve after that.
You're looking for the vertex when you say negative b over 2a. That's not going to help us here.
Yeah, but it's the square of that.
What do you, first of all, I know that you've got some great thinking going on there, but I'm not sure what question you're answering. Are you answering how to multiply this?
No, I'm answering
how to factor this? Okay.
Because if, like,
okay, so hang on, let me see what you're saying. So you're saying if I ask you to use the factor theorem to factor this, what's your brain saying to do?
So when you're trying to factor it, you're trying to find what does x equal that makes that thing 0.
Yeah.
So you do like whatever. It's like, so x is squared, so you do like square root. I did the square root negative or positive 3 over 2.
Yes, it's the same thing. Yeah. Mm-hmm.
But you actually like, so I made the formula for that, which is like n to the negative 1 b over a. Is that like an actual?
Okay, first of all, the reason why I didn't show you the quick way to do this, and I used the quadratic formula, which I don't tend to do, is because you see this is all you ever see instead of this. That's mistake number one. Okay, because so let's come up with your theory and let's see if it works. So your theory says, can I always do n root, yeah, of c over a? Is that your theory?
But it has to be -1 times c because
Okay.
if you're trying to like it has to be 0.
All right, but this,
So it has to be the opposite.
okay, so this is your theory, right? And that theory may give you one root, but not both of them. All right, so let's take a look. So the other way I avoided showing you how to do this, which is a lot easier to do, is to use this idea that you were taught way back when we solved quadratic equations. If you have something square equals a constant, then your answer is x equals plus or minus the square root of the constant. But what do we always forget? We forget the negative square root, right? And I'm hoping after all this work with polynomial functions, you're going to start to see when I see a 2 there, I got to have 2 answers. If anything will help you to remember this. So if you add 3 to both sides, you get that. And so this is where Christopher's idea of taking the opposite of whatever the C is here works, because you're adding it to the other side. You're going to change its sign. And then, of course, it's going to get divided by A. And there's Christopher's theory. The only thing wrong with Christopher's theory is he has to have a plus and a minus there. So that will work, Christopher. Because what do we end up getting here? 3 over 2. And now when you take the square root of both sides, the step you always want to forget is the square root of both sides here is not x. It's the absolute value of x, which is equal to the square root of 3/2. And when you have an absolute value equation, you know that the thing that can go in there can either be the positive square root of 3 over 2 or its opposite. And that's your 2 answers. Negative square root of 3 over 2. That's exactly the same as what I got here. Wait a minute, it isn't the same, you say. But let's take a look. These are exactly identical because I have the right to multiply a fraction top and bottom by 2 over 2, which is the number 1. And that gives me the square root of 6 over the square root of 4, which is square root of 6 over 2. So your quadratic formula and your square root, it's called extracting roots strategy, gives you exactly the same answers. Still doesn't answer how you multiply that. You should be able to multiply that to get back, and I really got to go on now. Yep, did you have a question about that, Patrick? Yes, you just FOIL this. These are conjugates. You're just going to get x squared and this thing squared, which is going to give you 3/4, and then you multiply everything by 2. You'll be all set. Anyway, or is it 3/4 or square root of 6/3? 6/4, and then when you multiply it by 2. Wait a minute, let's do this. 2 times x minus the square root of 6 over 2 times x plus the square root of 6 over 2. And you can multiply, your associative property says multiply any 2 first. These 2 factors look exactly the same except for one is minus and one is plus. So our middle term and our outer term go to 0. They're not going to become part of the equation. So we get x squared, take away the square root of 6 over 2 squared. That's what we get. And we're going to double all that once we simplify it. So we get x squared minus 6 over 4. And that gives us 2x squared minus 12 over 4, which is 2x squared minus 3. So we're right back to where we started. So Patrick, thank you for suggesting that strategy to solve that. Okay, so now let's move along. Did we get this done the other day? Okay, phew, good. All right, so all I'm going to do is encourage you. I know a lot of you leave these things blank. Do this activity. It's a great way to study for your next quiz and exam. All right. And I'll be happy to check it at any time, and you have the answers right here, so you can always check it on your own. So today we're going to expand our horizon. Our horizon has only been looking at real zeros. Real zeros. Today we're going to expand our horizon to look at zeros that are non-real. They have a real part and an imaginary part. So remember, our complex number system involves real and non-real numbers. So let's just quickly as we can, identify the zeros as you look across this polynomial. Now you should give me a hard time if I ask you to multiply that out. If you can multiply that out, you're in really good shape algebraically. But you probably don't want to take the time to do it, but it would be a fun thing to try. Anyway, I guess it depends on how you see fun. All right, so anybody tell me a zero? 1 0. Christopher? -3, because if I take this factor out and I set it equal to 0, I get -3. And let's classify -3. And when we classify it, we're going to say real, non-real, imaginary, complex imaginary, rational, and or irrational. So is it real or non-real first? Real number or non-real? Real. Is it rational or irrational? Rational. And for those of you who missed this on your take home on your project, I asked you to do integer coordinates. This is also considered an integer if we kept going down as far as we could. All right. Another 0. Can you help me with 1 0, Tyler, here? Any other one? You can pass. Anybody always has a choice to pass if you haven't been here. And okay. Anybody else? 1/2. Who said that? Tom, how'd you get that? Yeah. Equals 0. Is that the one you're doing? And if you solve this for x, you get x equals 1/2. Okay, good. And real or non-real? Real or non-real? Real. Rational or irrational? Rational. All right. Next one. X plus the square root of 2 equals 0. If I solve that for x, what do I get? Negative square root of 2, right. Negative square root of 2. Real or non-real? Real. Rational or irrational? Irrational. All right. We're moving along now. You're building steam out there. I can see it. X, take away the square root of -2 equals 0. X equals square root of 2. Remember, these are conjugates right here. These are conjugates. Remember, the word conjugate says the factors look the same, except one is an addition and one is a subtraction. So when you get one answer, you get its opposite. They come in pairs. So this is real and it's still irrational. Oh boy. To the next one. X take away 4 plus 5i is supposed to equal a 0. Who can take that one on? How are you going to solve for x here? Caitlin? I agree with you that x equals 4 minus 5i. But for some folks out there, could you tell them the steps for how you got to that answer? Okay, so you're thinking about what this would have to be so that when you subtract it, it's just the opposite of it, right? But if you were solving this equation for x, what's the series of steps you go through to solve for x? When you have a bunch of terms hanging on, what would you do? How do you isolate x here? John, can you help me with that? Can you tell me how I would solve for x here, what I would do, what the steps would be? Folks, Pass. Don't get nervous because you see a plus 5 right there. What if I said x minus 4 equals 0? What would be your first step? You would add what? If it was x minus 4 is 0, what would you do to solve? Solve the equation x minus 4 equals 0. What would you do? Just add 4. Thank you, Drew. So I'm going to add 4 to both sides. Okay, I'm almost home now. Look. Right? Don't let that little 5i freak you out. Now I want to solve for x. What's happening to x? It's having 5i added to it. How do you undo adding 5i? You minus 5i. Exactly, Tyler. So you minus 5i. And there you go. X equals 4 minus 5i. So that's one of your zeros. Real or non-real? Non-real. And it's complex imaginary. Okay, and here's the moral of the story, folks. Just like these two factors right here are conjugates of each other, look at these two factors. They're conjugates of each other. So once you know one complex imaginary zero or root, you get the other one simply by changing the subtraction to addition or vice versa. These always come in pairs. Always, always, always. Always. So, how do we use all this information now? Well, we're going to be able to solve even more complicated functions and graph them and do all kinds of fun stuff. What's the degree of this polynomial up here? What's the degree of this polynomial and how do you find it? It's 6 right, I hear, 6 right. So how did we get 6? I hear someone say 6 right. What you do? Yeah. 1. Okay. You add all those together. So let's add those. Well, 7. Okay, 2 plus 1 plus 1 plus 1 plus 1 is 7. And now how many linear factors does this polynomial have? Well, to see that, you notice that you've made your factoring a little more compact by writing x plus 3 to the second power. But if you wrote it out in all of its glory, you would say x plus 3 times x plus 3, and then you would have all these other linear factors. So you have degree 7. How many factors do you have if you count them all? How many factors? As linear, meaning to the first power. You've got 2 linear factors right here called x plus 3 squared. 2, 1, 1, 1, 1, 1, 1. How many is that? 7. 7 linear factors, degree 7. Now, how many zeros do I have? Oh, I didn't want that. Woo, look at all this stuff popping up. 7, because you count any zero that's repeated, like when you square it or cube it, twice. You count it as many times as its multiplicity. So you have the 0, -3, you count it twice. Counts twice. Because it's x plus 3, and it appears again, x plus 3. And then all your other zeros were only appearing once. You had 5 other zeros, so you have 7 zeros. So now, folks, you've got a little twist on that idea that we looked at, that if you have an nth degree polynomial, you know, remember your little theorem said you have at most n real zeros. And I told you, be careful, it says real. Now we're dealing with complex zeros. So now you can change that to say whatever the degree of your polynomial is, that's exactly how many zeros you have. Some of them may not be distinct. You might count them more than once. And that's how many linear factors you can have. So it's all equal to n now because we're dealing with both real and non-real zeros. So let's see how this plays out. Let's take a look at this this next function here. X cubed plus x squared minus 5x minus 2. We're going to find the exact values of all the zeros of this polynomial and then write it in completely factored form. Again, you have no way of factoring this polynomial with your regular tools available and skills. So if we want to find some factors for this, we're going to set the polynomial equal to 0, because we know when we set a polynomial equal to 0, whatever number, whatever value or values of x make that function 0 is going to then can be written as a possible factor for the polynomial. So first thing you would do is you would use your graphing calculator and you would try to find an integer that's a 0. So if you put this polynomial, I know in the old days graphing calculators were required, so they're not required anymore, so I just actually put the screen here for you. So if you put this function into your calculator in y1 and you graph it and you ask for a 0, you get 2, 0. So we now know that we've got a really pretty 0, that if I put 2 into this function, out would pop a 0. Okay, I get 8 plus 4 is 12. 12 take away 12 is 0. So that means since x equals 2 is a 0, if I work this equation backwards and subtract 2 from both sides, so I get my 0, there's my factor looking at me, x take away 2. So I can start off by saying I know the very first factor of this polynomial, and now I've got to come up with the factor that's left inside here. My leading coefficient is 1 here, so I don't have to worry about having anything else out there other than 1. How do I get this factor? And this factor inside has to have degree 2, because when I multiply x times x squared, that's how I'll get an x to the third. How am I going to get this factor inside? What do I got to do? Katie? Divide our original polynomial by its factor. So let's do that. We got to use long division. Or if you want, you can use your synthetic, because remember that the downfall of synthetic division is it only helps you when you can have a factor like this, x take away a number, or if it was x plus, your number would be a negative. But it's not going to help you if your only factor looked like 2x minus 3. Now, you could do some things to it, but you're not going to think about how to rearrange it. So learning the long division is helpful. Minus 5x minus 2. So your synthetic division over here would look like this. 1, 1, negative 5, negative 2. Those of you using synthetic. So let's do this real quick because we went through this the other day. X goes into x cubed, x squared times, and I get x squared minus 2x squared. I'm not going to do this as if I'm teaching it because we've already done that. And I get 3x squared minus 5x. X goes into 3x squared 3x times. And I get 3x squared minus 6x. Change my signs of both when I subtract. And I get x minus 2 left. And how beautiful is that? I get a plus 1. And notice this gives you a 0 when you subtract. You were already told 2 is a factor, so you shouldn't get anything else other than 0 when you do this. So now you have this. You can go inside here and fill it in with the answer. X squared plus 3x plus 1, and you would say, I'm done. And guess what? You are not done, because you have to continue to factor. And what you have inside here is a quadratic trinomial, so you have to factor this. Now to factor this, it looks like 8 part B that we started class off with. If I want to find a 0 of this, a factors of this, I have to find it zeros. So I better set that equal to 0 and use my quadratic function, so, quadratic equation. So what was it? X squared plus 3x plus 1? Okay, I've got to set that equal to 0 and find what values of x will make that 0 to get my other factors. So A here is 1, B here is 3, and C here is 1. So the quadratic function is the only way I can find the values of x that will make this 0. So I get the opposite of b plus or minus. B squared is 9 minus 4ac all over 2a. So that's -3 plus or minus the square root of 5 all over 2. So there are my zeros, my other two zeros. 1 0 is -3 plus the square root of 5 over 2. And what comes with it for free? Its conjugate partner, -3 minus the square root of 5 over 2. You just change addition to subtraction. So now I have my 3 zeros. My first 0 was 2. I got that off my calculator. My next 0 is -3 plus the square root of 5 over 2. And its partner, -3 minus the square root of 5 over 2. So there are my 3 zeros. Now that I know my 3 zeros, I can put this into factored form by saying x take away each one of these. So here, this is what it looks like in completely factored form. X take away a 2. X take away this thing, -3 plus the square root of 5 over 2. And then x take away -3 minus the square root of 5 over 2. And you don't have to simplify it beyond that. That's fine. The degree of the polynomial, original polynomial, is 3. If you look up there, it's 3. You have 3 linear factors, and you have 3 zeros. A pattern has been created. Degree n, the degree of n is 3. You have 3 factors. You have 3 zeros. So you always know now when you solve any kind of polynomial equation how many answers to be expecting. If you have degree 4, you can have 4 answers. Yeah, and you could have 2 if you had 2 perfect squares. When you factored it, you had 2 factors that were perfect squares. So this is what we now are starting to look at. This would be an answer where you had in all real roots, 1's rational and 2 are irrational. What about complex roots? Read this. This is given to you, but I want you to focus on this last one right here. These last 2 right here. If a plus bi, so you have a complex imaginary 0, a plus bi is a 0 of your polynomial function, then the imaginary number a minus bi is also a 0. That is, imaginary roots exist. If they exist, always come in conjugate pairs. Always, 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 always. You can't have one without the other. You might know some couples like that, right? You always see one, you never always see the other. Irrational zeros also occur in conjugate pairs. So if I tell you 1 plus the square root of 2 is a 0, guess what? 1 take away the square root of 2 is a 0 as well. And just think about your quadratic formula, what that looks like. It's always -b plus or minus the square root. Okay. So this is really important because if I tell you something like the next thing right here, find a 3rd degree polynomial function with real coefficients that has -3 and I as zeros. Stop right there. 3rd degree, n is 3. How many zeros should you have? 3. Do you see 3 zeros listed there? Do you see 3? How many do you see? 2. Go back to number 3. If you have an imaginary 0 or an imaginary root, guess what? It comes with a friend, right? So if I tell you that you have 1 0 that's a -3 and another 0 that's I, what is implied without it being said? What else is another 0? -I. These come in pairs, I and -I. Okay, so when you start to factor this, you put a out front because we don't know the leading coefficient, and then we just play our game here with our zeros. X take away a -3 becomes x plus 3. You can put a little 1 up there if you want to tell you that that's a linear factor. x take away I with the little 1 up there. And x take away a negative I becomes x plus I. Okay, now I still want to find A. How am I going to find A here? The value of A. I got to know a point that lies on this graph. Do I know a point on this graph, the coordinates of a point? William, what are they? -3, 0, right? All right, so if we put -3 in here, we get a 0 out there. That's true. But then we can't find the A because if we put either one of these in here, we're always going to get a 0 out here. So that's not going to help us find A. Do we know any point from any other information given? Andy?
You have the function of 1 equals 8.
Right, so I have f of 1 is 8. That tells me when my x value is 1, the output of my function is 8. So I know that point. When x is 1, my output is 8. So where I see f of x, I can put an 8. As long as everywhere I see an x, I put a 3 in there. Okay, and now I'm all set to finish this. 8 equals A. 1 plus 3 is 4. And now when I use my FOIL here to multiply that out, notice these factors look identical except of their operations. This is the difference of perfect squares, which means I'm not going to have a middle term here. I'm going to square my 1 minus square my I. And if you recall, I square was equal to -1. So where you see your I square, you can replace it with a -1. So you get 1 minus a -1 square is -1. 1 take away a -1 becomes 2. So you get 8 equals 4 times A times 2, which is 8A. So A is equal to 1. All that work just to find out that was a silly 1 right there? Bummer. That's how you would do it. Okay. So clearly, if it's been a while since you've worked with complex numbers, go back in your book, review complex numbers, multiplication with complex numbers. Okay, and I think that's it. Yep, it's time for your activity. So let's just do this first one together real quick because I don't want you getting stuck on this. I gave you little hints for each one. Write each of the following polynomial functions in completely factored form. Each comes with some suggestions on how to proceed. What kind of function do you have in A? What kind of function is that? Quadratic. So here's your parent function, folks, x squared. What's x squared plus 81 going to look like? What's that mean? It's going to go up how far, Kyle? 81, so it's way up here, all right? How many x-intercepts does that green graph have? The green graph? You're thinking why, right. How many x-intercepts? 0, because the x-axis is real numbers. So what are the zeros to this going to look like? Complex, real, complex, non-real. Can they be real? No, they're non-real. They're complex imaginary roots. Because to solve this for 0, you have the sum of two perfect squares, not the difference. So you've got 2 for the degree, 2 factors, you're going to have 2 zeros. And your job is to remember how to solve that quadratic equation. You can do it the short way and hopefully remember you got 2 answers, or you can use your quadratic formula. Okay, so that your goal here is to factor each one of these. The leading coefficient here is 1, so you're just going to have 2 factors here when you finish. Okay, so pick a couple of these and hopefully you can get a couple of these completed before the end of class.